Swayam Prabha. Digital India. Educated India.
So, what we will do is start with the Reynolds transport theorem again, okay, and then we will derive Reynolds transport theorem. We were halfway through that in the last class. So, the idea is we have a control volume. So, this is Reynolds transport theorem, okay, RTT. Now, like I said, what we want to do is we want to relate changes in control mass to changes in control volume. That is the idea, okay. And with that objective, I am choosing this as my control volume, okay, and this is the control surface. The boundary of the control volume is my control surface, okay. What is inside the control surface is my control volume, okay. So, this region, the whole thing inside is my control volume. So, at time t, I say the control mass occupies the control volume, okay, and because there is flow, what is going to happen is the control mass, control volume, remember, is a fixed in space. So, that is not moving, control volume is fixed, but the molecules which are inside, they are moving. So, some molecules would have left the control volume, new molecules would have entered the control volume, okay. So, this is the dashed oval at time t plus delta t, the dashed oval is the region occupied by the control mass, okay. So, at time t, control mass occupies the solid oval, at time t plus delta t, it occupies the dashed oval. Mass is all those molecules, all the particles which are focusing on, okay. Now, what we wanted to do is, for the sake of simplicity or making arguments more concrete, I divided this whole thing into 3 regions, 1, 2 and 3, okay. 1 and 2 are regions occupied by the control mass. 1 and 2 is the 1 and 2 basically, but this is by control mass at t, and 2 and 3 are regions occupied by the control mass at t plus delta t. So, basically I wanted to ask what is the rate of change of property of the control mass in the control mass, okay. So, I am using this symbol here. This is limit of the property in the control mass at t plus delta t minus NCM of t divided by delta t in the limit delta t tending to 0. This is the rate of change of property in the control mass, okay. And remember, control mass is occupying at time t plus delta t the regions 2 and 3. Okay. So, I am going to write this as limit delta t tending to 0, and because in over regions 2 plus 3, I wrote this as eta rho dV. Okay. And this is evaluated at t plus delta t minus this is over regions 2 plus 1 eta rho dV, this is at t. So, what is eta? Eta has a specific property, n is the extensive property. So, eta is n per unit mass. Okay, rho dV is my mass, rho is my density, dV is my volume element. So, rho multiplied by dV is my mass, and so n dn, okay, I will come to that later, this is by delta t, and this I write as eta, remember, is n divided by mass or n by rho v, and because I am integrating it over the volume, because I can have changes in density, changes in eta everywhere, I am integrating it over. Okay. So, basically this is my extensive property which is dependent on mass, and eta is independent of mass because it is an intensive property the way I have defined it. Okay. So, n divided by rho v is this. So, rho dV is eta multiplied by rho multiplied by dV is my dn. Okay, and I am allowing for the velocity to change inside. Therefore, I have to integrate this over the entire region. I am not assuming it is constant everywhere. Okay. So, at different volume elements, my density can be different, my eta can be different. So, it is possible that in the control volume, the density and the intensive property can vary from point to point. Okay. So, that is the reason we are not looking at just taking average value, but we are looking at finding the property by integrating it over a small control volume. Okay. That is what we have done, small element, sorry, small element. Okay. Now, so this accounts for the fact that eta and rho can vary spatially. Okay. In regions 2 and 3, there can be eta and rho varying spatially. So, as far as this property is concerned, I am just integrating it over this. Now, I think I am going to get rid of this diagram. I am going to group the regions 2 together and regions 3 and 1 together. Okay. So, this is, oh, I should have kept the diagram, limit delta t tending to 0, triple integral over 2 of eta rho dV at t plus delta t minus triple integral eta rho dV at t. Okay. What have I done? This is region 2. So, this region 2 and this region 2 I am keeping together, plus integral eta rho dV over region 3 minus integral over region 1 eta rho dV divided by delta t. Okay. Now, what I want you to do is, and this all, there is a divided by delta t here also. in the limit of delta t tending to 0, okay, we are calculating this first two terms in the limit of delta t tending to 0, the region 2 is going to coincide with my control volume, okay. Region 2 as delta t tends to 0, region 2 will pretty much occupy my control volume. So, basically what I am going to do is I am going to write this, let me call this guy, okay. So, as delta t tends to 0, region 2 occupies my control volume, okay. So, this is basically going to be control volume, okay, and I have this will be d by dt, the first term, the first two terms on the right hand side, these two terms, they are nothing but d by dt of integral over the control volume of eta rho dV, okay. So, I am identifying these two terms as rate of change of the property in the control volume, okay. This is the right hand side, left hand side is ddt of NCM, I keep it as it is, I am only talking about the right hand side now. So, this is the rate of change of property in the control volume, okay, because as delta t tends to 0, region 2 is going to be the same as my control volume. Now, what does this term represent? Eta rho dV over region 3, that is the property which has left the control volume, which has gone out of the control volume because of the flow, okay. This property here represents the property which has come into the control volume because of the flow. Unfortunately, I removed that figure, but 3 is the region which has left the control volume, mass occupied by the control volume, okay, outside. So, this the third term represents, so I am going to write it in English now, triple integral over 3 eta rho dV is the property which has left the control volume across the control surface, and triple integral over 1 is eta rho dV is property entering the control volume across the control surface, okay. So, this is my out, this is coming in, this minus this is the net rate at which the property has left the control volume, okay. So, integral d over region 3 eta rho dV minus integral over region 1 eta rho dV divided by delta t is, because of delta t, it tells me the rate at which the property has left the control surface, total rate at which the property has gone out of the control surface, okay. Has left the control surface, okay. This is just the property leaving divided by delta t is the rate at which is going out, okay. So, this is the rate of efflux, rate of outflux, rate of outflow of the property from the control surface. So, what I want to do is put these terms together. So, now I am going to write that equation NCM equals d dt of integral over the control volume of eta rho dV, okay, plus rate of efflux of the property over the control surface, okay. I mean the other two terms, the region 3 minus region 1, I showed you physically what it is. So, I am just writing it in English now, I will convert that to mathematical representation. So, now if you have, this is a control surface, okay, and you take an area element dA, dA is the area element and it is a vector, okay. The direction of the vector is the direction of the outward normal. So, you look at this element, this is the direction of the outward normal, that is the same as the area of dA. So, I mean the direction of dA. So, what I am saying is the direction of dA, which is a vector, is that of the outward normal, okay. Now, across the surface we have flow, so there is a velocity, okay, across the control volume, across the control surface we can have flow. So, what does V dot dA represent? V is the velocity at the surface, V dot dA represents the volumetric flow rate of the fluid across that area element. So, V is a vector, dA is a vector, V dot dA tells you is a scalar, gives you a volumetric flow rate, okay. So, this is the volumetric flow rate across dA, and if I want to get the mass flow rate, what do I have to do? Just multiply that by density, rho V dot dA, and remember density is a scalar, is the mass flow rate out of the control surface across dA, okay. And what I am interested in is the property. So, I know the mass flow rate. So, if I multiply it by the intensive property, I will get the total, if I multiply this by eta, I get the total property which is leaving the control surface, okay. Eta rho V dot dA is the property leaving the control surface through dA, okay. That is my third term, rate of efflux, but this is only across the element dA. I want it across the full control surface. So, what should I do? I should integrate it over the entire surface, okay. So, if I want to integrate this thing over the control surface dA, this is the total efflux across the control surface, okay. dA is just a small element in the control surface, okay, and if I integrate this thing and I found out what the property efflux was across this, so eta rho V dot dA, I want it across the full control surface. So, I am integrating it throughout the surface. That is my third term. This is my third term here, rate of efflux of property across the control surface. So, all I have to do is substitute this mathematical expression there, and I get d dt of NCM equals, I am going to do a small trick here. dV plus integral over the control surface of eta rho v dot dA. Okay. And this particular thing which I have written at the very end, this is your Reynolds transport theorem. Okay. This is it is relating changes in the control mass to changes in the control volume, okay, and to and this is the property leaving. I just want you to I told you earlier that there is some kind of an analogy with this thing we derived earlier for a particle dt by dt equals partial derivative of t with respect to t plus v dot del t. We had derived this thing when we were trying to relate Eulerian and Lagrangian approaches. Okay. So, this is Lagrangian, this is Eulerian. Eulerian means I am fixing my attention at a particular point. Same thing here, this is for a mass, this is something like my Lagrangian, this is my Eulerian because I am now looking at a fixed control volume, fixed region in space. Okay. This is Eulerian and that is the efflux and that is associated with this convective term there. Okay. So, whatever you did for an infinitesimal volume or a very small element, small molecule and a small area, we have extended to a region in space now. Okay. So, I mean you people have to sit and the best way to understand concepts is to try and look at analogies which help you understand them better. Okay. Otherwise, I mean you will appreciate certain things. If you are confused about how things are in a particular relationship like Reynolds transport theorem, it is good to go back and see if there is some analogous concept somewhere else which you understand better and then try to relate this new concept to that to improve your understanding. Okay. And that is what I am trying to do now is just do that, try to make connections between that total derivative and partial derivative what you did in mathematics the same thing here Euler's acceleration formula, okay, and Reynolds transport theorem. Okay. So, this is basically Reynolds transport theorem which you have seen. I did a small thing here, I made this partial because now I am instead of putting it as a total derivative, the reason I made it partial is because we are looking at a fixed region in space. Okay. Because we are looking at a fixed region in space, everything the spatial coordinates are fixed. So, I made it instead of total derivative, instead of d I put it as a partial derivative. Okay. So, you realize that this is for a fixed region in space. So, this eta, supposing I am interested in conservation of mass, what will eta be? Eta will be 1 because it is mass per unit mass. Okay. Supposing I am interested in conservation of momentum, then I instead of wherever eta is there, I will put momentum per unit mass which is velocity. Okay. So, basically I am saying eta is 1 for conservation of mass, it is velocity for conservation of momentum. Okay. What I want to do is I want to show how we can write the conservation of mass now. Okay. I want to take Reynolds transport theorem and illustrate it for conservation of mass. Okay. So, all I have to do is put eta equal to 1, conservation of mass. Okay. And I am going to put eta equal to 1 in my Reynolds transport theorem. Then I get d dt of NCM equals partial derivative with respect to time of integral over the control volume rho dV, okay, plus integral over the control surface of rho v dot dA. The Reynolds transport theorem, I have only put eta equal to 1. Now, I have this volume integral, okay, and because this control volume is fixed in space, it does not change, the control volume is not changing with time, okay, it is fixed. So, I can interchange the integration and differentiation, I can move this derivative inside, okay, because this is equal to triple integral over the control volume of d dt of rho dV plus integral over the control surface of rho v dot dA. Why can I do this? Because the control volume is fixed in space, it does not change with time, okay. Now, this is a volume integral and this is a surface integral. I can convert surface integrals to volume integrals. I mean, you must have done this in mathematics. There is a divergence theorem, the Gauss divergence theorem, which allows you to convert a surface integral to a volume integral, okay. So, I am going to use that now. So, whatever divergence theorem you did in your maths course is relevant here. So, if I want to convert this, because I want to combine these two into one integral, okay, I want to convert this, convert the surface integral to a volume integral using the divergence theorem, okay. And what do we have? Over the control surface, rho v dot dA will be over the control volume of divergence of rho v dV. This is the velocity vector. This is again velocity vector, okay. I mean, I just want to, because I want to differentiate between the v which is velocity and the v which is the volume element, okay. So, now this is also a volume integral, this is also a volume integral, I can combine the two volume integrals because they are over the same volume, the control volume, okay, and I get d dt of NCM okay. So, I have combined the two integrals, two volume integrals into one, d rho by dt plus divergence of rho v equals dV. So, now I want to talk about the left hand side. Left hand side tells me what is the rate at which the property in the control mass changes, okay. Remember, we are talking about conservation of mass. So, when you are talking about conservation of mass and the control mass is by definition has fixed mass, okay. That is how we identified control mass. Control mass is basically a collection of molecules, particles where the mass does not change, okay. It can move around, it can go out of the control volume, but the mass in the control mass is fixed. So, the left hand side d dt of NCM has to be 0 because the mass, because I am talking about conservation of mass now, Okay. So, this left hand side here is 0 because for a control mass rate of change of mass equals 0. Okay. And what this means is I have 0 equals triple integral over the control volume of d rho by dt plus divergence of rho v dv. Okay. The next argument I am going to make here is that I can choose my control volume to be infinitesimally small. See, there can be variations everywhere of rho, velocity in my control volume. Okay. And if you really want to capture those variations, you will possibly have to choose a control volume which is small. So, this particular relationship is valid for any control volume, and if you choose your control volume to be infinitesimally small, then you can write this as this term multiplied by dV. It is not dV is infinitesimally small, but it is not 0. Okay. So, because this can hold for any control volume, okay, it is infinitesimally small. What does this mean? It means that thing you are integrating has to be 0 at every point. So, since this is valid for any control volume, we can choose it to be small, I mean infinitesimally small, and for every control volume it should be 0. That means this guy what we are integrating has to be 0 at every point. Okay. So, this implies that d rho by dt plus divergence of rho v equals 0 at every point in the control volume. Okay. Now, if that is not clear, you can just think that alternatively we can write triple integral of dV as d rho by dt plus divergence of rho v multiplied by dV, because this is a very small thing, very small control volume. Okay, you can treat that as a constant inside the control volume and pull it outside, and this is not 0, therefore this has to be 0. This is not equal to 0, therefore this has to be 0. This implies this is 0. Anyway, just think about what I have said. This is a very standard argument which is made most of the time. Okay. And what we have derived is basically the equation of continuity. So, this is the equation of continuity, which is a mass balance, which is a local mass balance. It is a differential form of the mass balance, which tells you how the density, how the velocity are going to vary spatially and with time. Okay. So, this equation is the equation of continuity. So, this is the equation of continuity or conservation of mass. So, if you have there are some simplifications which we normally resort to. If you are talking about liquid, okay, then we treat the liquid as being incompressible. So, this becomes for liquids rho is equal to constant incompressibility. Okay, that is the typically liquid density do not change. So, how does this simplify? Density will not change with respect to time, it will not change with space. So, density is constant, I can pull it outside my divergence, my operator, and this simplifies to divergence of V equal to 0. Okay. If density changes, if you have a gas, you have a compressible liquid, compressible fluid, then you have to use this full form. Okay. But if density is constant, you can say that. Now, some of you may have seen a derivation of this by doing a shell balance, where you take a rectangular box and then you look at what is coming in, what is going out, and accumulation and all that. So, this is, you can do it that way, but we can do it this way also. Okay. This is possibly a more elegant way, you might say it is more confusing. It will be confusing for 2 days, after look at it 2 more days, it will become very clear. Okay. So, keep looking at the equations. The other thing I want to talk about is, when you talked about this conservation of mass, normally you are used to writing this form of the conservation of mass equation. So, accumulation equals in minus out plus generation. Okay. This is used commonly, right. I mean, somewhere in your undergrad course you must have used this accumulation equals in minus out plus generation. This is also a conservation of mass, this is also a conservation of something in a. So, what is the relationship between this and the different terms we saw in the Reynolds transport theorem? This accumulation term is associated with the fixed control volume, that is what is happening in your CSTR, in your tank. Okay. This is your in the control volume, that is the Eulerian thing. In minus out is a net, if I write it as out minus then net outflux. So, the right hand side is the negative of the net outflux. Okay. This is minus of the outflux from the control surface. Okay. You had a term which was talking about the outflux from a control surface, right. That is this term, out minus in, and the only one more thing is remaining. What is that? That is the Lagrangian, the control mass. What is associated with the control mass? This is the Lagrangian or associated with control mass. So, 3 terms in the Reynolds transport theorem, I am trying to identify those 3 terms with what you have seen before. Okay. So, the Reynolds transport theorem is just a different way of writing accumulation equals in minus out plus generation. Okay. Accumulation is the triple integral over the control volume. This is the derivative over the control mass, the one we had on the left hand side when we derived, and this is the term which is associated with the control surface, what is going out of the control surface. Okay. So, that basically is trying to put things in perspective of what you know, what you have seen today, so that you can make these connections. Now, conservation of momentum, okay. That is the other conservation law that we have, and here all you have to do is go to Reynolds transport theorem and put wherever eta is there, you put the velocity v, okay. So, d dt of NCM, n now is my momentum of the control mass, is equal to d by dt of control volume, eta is eta rho dv, no. What have I done? Wherever eta was there in the Reynolds transport theorem, I have substituted the velocity vector, okay. And I am going to do the same thing I did earlier, pull the eta, pull this derivative inside the control volume, the justification being that the control volume is constant. See, if the control volume is changing with time, then you have to use what you learned in your calculus class, Leibniz rule, to take into account that the entire limits are changing with time. Here I am integrating over a limit which does not change with time, so I can pull it inside, okay. And again I am going to convert the surface integral to a volume integral. So I am going to do two steps in one shot, okay. Pull it inside d by dt of rho v plus, okay, let me do this one step at a time, divergence of rho v v dv. So I have converted the surface integral to volume integral, I have pulled the time derivative inside, and now I combine these two volume integrals to give me okay, divergence of d by dt of rho v plus divergence of rho v v is that. So, this term that you see on the right hand side here is actually what you see on the left hand side of the Navier-Stokes equations. The Navier-Stokes equations, you will write rho dv by dt. I mean, we have to make some manipulations, but you will see that this is the these are the terms associated with the usually associated with the left hand side of the Navier-Stokes equation, okay. These are the terms which are on the left hand side of the Navier-Stokes equation, okay. We will see that. I am just telling you that we are pretty much very much close to this thing, but what about this guy here? This is basically talking about the rate of change of momentum of a control mass, rate of change of momentum of a control mass. What is that equal to? From Newton's law of motion, the rate of change of momentum of a control mass is nothing but the forces which are going to be acting on the control mass. So, this is what I told you earlier. The Lagrangian approach control mass is where the fundamental laws are, okay, and I want to use that, but I want to focus on fixed regions in space. So, I need to do the control volume, and that is the relationship which I have. So, now from the Lagrangian approach, this guy on the left hand side are my forces, okay. So, d dt of NCM equals forces acting on the control mass occupying the control volume from Newton's law. Okay. And basically there are two kinds of forces that we are looking at. One is the body force, which is going to be there because of gravity. So, what is going to be the body force? It is just rho g dV. Okay. The body force is going to be, for the entire control mass, is going to be integral over the control volume of rho g dV. Control mass is occupying my control volume at time t, right? That is how I identified my control mass. So, this is rho g, so dV, and then have the surface forces, because on the control surface there is going to, so that is what we have to talk about next. Plus we also have surface forces across the control surface, which we need to include. So, the question is how do you do that? And I might see you may are used to finding out divergence of rho v, because del is a vector, rho v is a vector. Now, I have divergence rho v v. So, the question is how do you calculate this term? So, what I intend to do is take you a little bit through some basic notation and how to calculate some terms, okay, in vector calculus in the next class, and then talk about how the surface forces are calculated. These surface forces will be your pressure force and your viscous force, okay, and then the Navier-Stokes equation is done. Thank you.